Alright, so now that we finished with infrared spectroscopy, we're going to get into another technique that also will help us to identify compounds. Now, mass spectrometry works in a very, very different way from infrared spectroscopy and also gives us very different information. So mass spectrometry, unlike any of the other techniques that we'll learn, is actually a destructive technique. And what we mean by that is that when you take an IR spectrum, you put your sample on the instrument, and after you're done taking the spectrum, you can recover your sample. You can get it back. You can use it for something else. But mass spec actually destroys the sample that you use. Now, it turns out this isn't a very big deal. As you'll see and learn more when you actually use the instrument. In general, it requires about 1 microliter of solution, and that's of a very dilute solution already, so typically requires nanogram, 10 to the minus 9 gram quantities. So that's one of the big advantages of mass spec. So yes, it does destroy your sample, but we're only talking about nanograms of our sample, and that's just a tiny, tiny amount. In fact, that actually makes mass spec more sensitive than a lot of our other techniques. For IR or NMR, you need at least milligrams, so 1,000,000 times more. But what does mass spec do for us? So it uses ionization we can measure the actual mass or the molecular weight of a compound. Now, it's not going to give us the full molecular mass or the full molecular weight for every compound. We'll talk about some of those cases later. But it does give us information about the mass of the compound, even if it doesn't. Alright, so how does this work? So we're going to talk about sort of some of the very generic, basic type steps that a molecule is going to go through once you inject it into the mass spec. So we start by injecting the sample. And after that point, so inside the mass spec, it's at very, very low pressure, 10 to the minus 5 torr. For reference, standard pressure is 760 torr. So very, very low pressure. What this does is that in addition to the high vacuum, the sample is heated. And so for virtually any sample that you put in, and you usually inject these in solution, it is two things. First of all, the solvent just ends up getting boiled away. But the more important piece is that the molecule is almost always going to be in the gas phase. And so once it's in the gas phase, we use a carrier gas to transport the molecule. Now, this carrier gas is often one of the most annoying parts of mass spec these days. Why is that? Well, the most common carrier gas that we use is helium. And you may or may not be aware that there's actually a shortage of helium in the world. And so it used to be one of those things that you called up your gas supplier and said, I need a tank of helium, and you'd have it tomorrow. In the last 10 years, the price of helium has probably tripled, and sometimes it takes us weeks or even longer to get just a single cylinder of helium. All right, but what happens at this point is our molecule that we want to measure is in the gas phase, and it's being carried through the mass spec. So if this is our compound RH, it's going to start getting hit by high energy electrons. By high energy, we mean about 6,700 kilojoules per mole. And these will knock out a valence electron. So the result here is that we end up with a cation. Now, in addition to that, we want to remember at this point, we're at extremely low temperature or low pressure, so high vacuum, or at high temperature, typically 100, 200 degrees Celsius, and high energy. And so the result of these conditions is that the molecule itself may break apart into fragments. And as that happens, once we actually start looking at some spectra, and we'll just put one up here for a moment. You can see we don't get just one peak for a compound, we get a whole series of peaks. Now, we'll come back to this spectrum in a few minutes and talk about what it actually means more. All right, so now what we've got is, in some cases, the molecule is still intact, just missing an electron, so we've got an ion. And in other cases, we've got fragments of the molecule. So anything neutral is discarded. And the resulting ions are sorted by their, what we call their M to Z, which is their mass to charge ratio. Now, in almost every case, the charge ends up being 1, so this M to Z ratio is really just the mass of the piece of the molecule. And then the computer records the ratios and their relative percentages, and that's what gives us a spectrum. So once we're looking at the spectrum, what do we actually see? Well, the most important peak that we see in most spectra is what we call the M+. So M here refers to the mass of the full compound. So M+, or the parent peak, is the mass of the entire molecule. And usually, this is the highest mass in the spectrum. In addition, we'll see peaks that are referred to as fragments. And these peaks are usually designated as M minus something. So these are pieces of the molecule. And in some cases, we'll be able to identify every single fragment we see. And in some cases, we only see small pieces. We are only able to identify some of them. Because again, the conditions that mass spec occurs under, high temperature, high energy, and high vacuum, allows for a lot of really weird things to happen to molecules. Now, what this M minus means is that's how we sometimes designate what the peak is. So, for example, if a molecule loses a methyl group, or a CH3, how much mass has it lost? Well, we know that carbon is 12, each hydrogen is 1, so at that point we know we've lost a mass of 15. And so we would say that the peak that represents the loss of the methyl group is the M minus 15 peak, because it's lost 15 from its mass.